In general, we can find many values x where x is equivalent to a mod n, or again, equivalent or congruent to a mod n. Because equivalence mod n is an equivalence relation, then if x is equivalent to a mod n and x prime is equivalent to a mod n, then x is equivalent to x prime mod n. So, if there are many solutions, always ask if one is preferred or canonical. Is there a preferred solution? So let's look for the least. Since x and x prime are integers, let's see if we can find the least non-negative value equivalent to a mod n. Since x equivalent to a mod n means n divides x minus a, then x minus a is some quotient times n, or x is qn plus a. But this looks a lot like our definition of quotient and remainder. In fact, if a divided by n is b with remainder r, then a is qn plus r, and so a minus r is qn, and so a is equivalent to r mod n. This gives us a useful theorem. A is equivalent to r mod n, where r is the remainder of a divided by n. So, for example, we might try to find a solution x equivalent to 57 mod 11. One possibility is to find x where 11 divides x minus 57. But we could also find 57 divided by 11, which will be, and since the remainder is 2, then we know that 2 and 57 are equivalent mod n. So let's do some arithmetic. Since the end result will always be an integer, we can try to simplify it by finding the least non-negative value equivalent mod n. We say that we are reducing mod n. So what if we add or multiply two integers mod n, and can we divide? Well, never divide, but can we? Well, let's add. Since 25 and 37 are integers, we could just add them. We then find, and so 25 plus 37 is equivalent to 2 mod 12. Likewise, we can add, then reduce mod n. Now, this seems to be a lot of work since we have to do the addition and then reduce mod n. So remember, all human progress comes from being lazy. Well, let's see what would happen if we reduced first. So for working mod 12, let's divide by 12 and keep track of the remainders. And we find, and so 25 and 37 are equivalent to 1 mod 12. And this suggests that maybe if I add 25 and 37, I might get the same result as if I add 1 and 1. In other words, maybe 62 is equivalent to 2 mod 12. And in fact, that's exactly what we found. And this suggests the result. If A is equivalent to R1 and B is equivalent to R2, then the sum is equivalent to the sum R1 plus R2. Let's go ahead and prove this. Since A mod n is R1, then we know the difference is something times n. And likewise, we know that B minus R2 is something times n. So if we find the difference between the sum of A and B and the sum of R1 and R2, we get, which is n times something, and so the sum of A and B is congruent, there I said it, to the sum of R1 plus R2. And this is useful because it means we can add something horrible like this much more easily. So we could add these two numbers, or we could note that 31,947 is congruent to 2 and 193,14 is congruent to 4. So their sum is congruent to the sum. And so we get our ability to work with numbers reduced mod n leads to a useful feature of arithmetic mod n. When working mod n, you can always work with integers between 0 and n.